Hi everyone, hi BC students. Okay, so basically I am going to run through the entire homework packet and I'm just going to adjust the questions so that they're like similar but not exactly like the homework packet that you guys are doing. But basically, like, if you want to work through this packet problem by problem with me, you should be able to do every problem with like no issues. I'm literally going to go through the entire packet and like do problems that are extremely similar. So, and I will explain them as I go. I'm going to do them kind of quickly, but I'll upload this to YouTube so you can probably pause and whatnot as we go along. Okay. Well, okay, so the first thing that was there was the limits review, and you'll notice that this graph is different from the graph that I uploaded for your homework packet, but same concepts apply. So consider the graph of the function f of x shown below where y equals f of x. Okay, cool. Just tells us that this function is f of x. Evaluate the following, f of 1. So f of 1, notice this isn't a limit. We're literally just asked to plug in 1. So when we plug in 1, we'll look here, right? That's where 1 is, right? We'll notice that it looks like it's going to here, but there's a hole in the graph actually. And f of 1 is actually located down here because that is a filled in hole. So that is where f of 1 is actually equal. So it's equal to -1. The limit of f of x as x approaches 1. So this is now asking us the limit. So it's a two-sided limit, right? Because it doesn't specify which side. So we automatically assume when it doesn't specify like plus or minus here, right? That it's a two-sided limit. So as it approaches 1, this is just the general definition. Like the limit is what the value of function approaches as it approaches like this value here, a. So it's approaching, you can see from both sides, going to 1, right? Even though f of 1 is down here, the limit is approaching 1 because they're like convening onto that point. So it is equal to 1. The limit of f of x as we approach, okay, I think I edited this wrong. There should be 0 and the minus should be here. So 0 from the left, right? That's what it's saying. So as we approach from the left, we're approaching 0, right? Approaching right here. That's where 0 is, right? In terms of this, that's where 0 is. Approaching up, it looks like we're approaching -1. Cool. From the left, we're approaching -1. Notice if we were approaching from the right, it would be from here, we'd be approaching 3. And okay, well, that's the next question is asking just the limit of f of x as x approaches 0. Well, this again, remember, it's just two-sided limit. So we're going to look at the same one as before as x approaches 0 from the left. Cool, it's going to -1 from the right, though. Like I just said, it's going to 3. Well, what do we know about a limit? What if the two sides approach different values? Well, then we know that it doesn't exist, right? For a limit to exist, they have to approach the same value from the left and the right. Cool. So that should take you through the first problem. Evaluate the following limits and box your final answer. Okay. I might either adjust these problems or just kind of give a hint for each one on what you should be doing. So the top, this one, right? You'll notice that, yeah, I'm going to come up with a problem. Let's do x squared plus 5x plus 4 over x plus 1. And it will be, as the limit approaches x for -1. Okay, so you'll notice right here, we plug in -1, right? If I plug in -1, I'm going to get -1 plus 1 in the denominator, which is equal to 0. Well, that's very bad. Again, whenever we have 0 in the denominator, that is very bad because that means the function is undefined. And we do not want that. We want to see if we can avoid that. And again, with these, it should be pretty obvious at the start when you see this type of x squared and then a different like x value on the bottom. Our first instinct should always be to factor it. So let us try to factor it. X squared plus 5x plus 4 on the top. That would factor it to x plus 4, x plus 1, right? Limit is x approaches -1. Now in the denominator, we're going to also have x plus 1, right? And then look, oh cool, x plus 1 can cancel. So now we have x plus 4. And then we're just going to plug in, so that's -1, we're just going to plug in -1. So -1 plus 4 equal to 3. So that is our answer for this one. The same technique can be used for this problem. So let's see, as x approaches infinity, let's do 4x to the third minus 3x plus 2 over x to the fifth plus 8. So very similar, but not exactly the same. So remember, anytime we see x is going to infinity, you know that we're dealing with the end behavior limit, end behavior. So we're curious how this function acts at the way ends of the graph, like way positive infinity, negative infinity, stuff like that. So our first rule is always to isolate the dominant terms. So what are the dominant terms in the numerator? Well, 4x cubed, that's pretty clearly the dominant term. The other terms are 3x and 2, well, negative 3x and 2. And then the other dominant term in this case is x to the fifth. One thing to remember for these problems is that we always have to take into account signs too. Luckily, well, so let's say this 3x was to the seventh and this was the dominant term. Well, when we circle this as the dominant term, we have to take into account the negative sign. So the dominant term is actually negative 3x to the seventh in this case. So that is something to remember. In this case, it's not, it was squared. So let's just rewrite the limit as dominant terms. So just only take the dominant terms, right? X to the fifth. Well, let's see, x is going to infinity. Which one's larger? Well, x to the fifth is obviously larger than x cubed. So we're going to have a large number on the bottom and a small number on the top. So that is going to be going to 0. Notice it's going to 0, so we don't really care about signs because 0 or negative 0, it's the same thing. If it was going to infinity, though, we might have to worry about what sign. So, for example, if this was negative 4x cubed, and this number was larger, like 7, like we looked at before, this would be going to negative infinity. Whereas if it was positive 4x, it would be just going to regular infinity. So that is something to take into account. In this case, it's going to 0. In the original problem, I don't know, could be whatever, could be going to any number. Okay, wow. What I do not know what happened here. Hopefully that was, let me check the original. Oh, okay, something just must have happened. Okay, so this originally was negative 4x cubed. Okay, so this is going to negative infinity. I'm going to rewrite this as the sine of x to negative 7x to the fifth over 4x cubed minus 1. Cool. Okay, so this is going to negative infinity. Well, it's also an end behavior limit again, and limits going to infinity or negative infinity are all end behavior limits. So let's isolate the dominant terms. Well, sine of x or negative 7x to the fifth. Remember sine of x and cosine of x? Remember how they act? They just go like this, infinitely. They never stop. Going way down, they constantly just kind of waver back and forth. between 1 and -1. So it's obviously not going to be sine of x. Our dominant term is going to be negative 7x to the 5th. And notice I did circle the negative because the negative is part of the 7. It's not just 7x to the 5th, it's negative 7x to the 5th. In the denominator, I have -1. That's obviously not the dominant term. And then I have 4x cubed. That obviously is the dominant term. So I'm going to rewrite this as limit as x approaches negative infinity of negative 7x to the 5th over 4x. Well, the first thing we can see is which one is larger and which one's smaller. Well, x to the 5th is obviously dominant over 4x, so we're going to have large over small. Now we're going to negative infinity, though, and we have a negative sign. So this is where stuff like this gets kind of confusing. We have to take into account all these signs. So we have a negative sign up top, right? So let's pay attention to signs. I'll write that. This applies for every infinite limit. It's just this one, it was pretty obvious that everything was positive. It's going to positive infinity. So we know our answers, like going to be positive, plus it's going to 0, so it doesn't matter. But so this one's pretty easy. But this one has a bunch of different like negative signs and then negative infinity. It's kind of confusing. So pay attention to signs. Well, so the top we have a negative, right? And then x to the 5th, if we plug in negative infinity, a negative number to the 5th power, well, that's also going to be negative. Remember, a negative number squared is positive. A negative number cubed, a negative number squared is positive. A negative number cubed would be negative, right? So a negative number to an odd power is always going to be negative. So we have two negatives on the top, and then the denominator is just straight up 4x, and then x we know is negative, going to negative infinity, so it's also going to be negative. So at the top, it's a positive, negative times a negative, so we're actually going to get a positive, and this is all divided by negative, and a positive number divided by a negative number is a negative number overall. So large, small, going to infinity, but we're also going to negative infinity, because we're taking into account the signs. I don't think the original problem is as confusing, but the same concept. You have to take into account the signs and think about how the negative infinity fits within like the problem. Okay, cool. Okay, so this is the part where I think I probably could have taught more in depth for continuity and differentiability. I feel like we covered it like casually, but we didn't cover the mathematical aspect of it as well as we could have. So this section in particular might be useful for people to watch. But quick refresher, a function f of x is said to be continuous at x equals a if the limit of f of x as x approaches a is equal to f of a. Now remember, what does this mean, right? This aspect is really important. The limit of f of x as x approaches a. That means the two-sided limit must exist, right? So this really means as x approaches a from the right of f of x, this must equal the limit as x approaches a from the left of f of x, right? For this to be true, right? For that to even exist. And all of this must also equal f of a. So there's kind of like three components to the problem. There's these two have to be equal, or you can, so you could think of this like this has to exist, right? So these two have to be equal. This has to exist, f of a has to exist. And then the final component is that they must all equal each other. These two, everything must equal. So these two must equal each other. So depending on which way of thinking about it is easier for you, I mean, they're the same way of thinking about it. So next, the function f of x is said to be differentiable x equals c if f prime of c is equal to limit of blah, 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 blah. Now, I feel like we rarely use this in calculus, so I'm not sure how worth it is to really remember this besides just memorizing this notation, because you might need to use a notation. but you can just kind of solve for it later if you really need to use it. But the whole idea of differentiability is, remember, the same idea. So this is the limit definition of a derivative, right? So again, limit as h approaches 0. This is a two-sided limit, right? So what it's really saying is from both sides, left and right, the function must be differentiable. So what does that really mean? It means from both sides, convening at a point, we must be able to take the derivative of the function. So I'll show what that means in a second. Now, let's get started on actual problems. Which of the following graphs are continuous at x equals 1, and which of the following graphs are differentiable at x equals 1? So these are the same problems, so I'm not going to actually solve them, but I'm going to remind you that for visually, right, graphs are continuous if we can draw without picking up our pen. So kind of, can you, like, just imagine you drawing all these. Can you draw this one without picking up your pen? You tell me. Can you draw this one without picking up your pen? You tell me. So if it's continuous, you can draw without picking up your pen. If you can't do that, then it's not continuous. Now, which of the following graphs are differentiable at x equals 1? Well, to be differentiable at x equals 1, remember we have certain exceptions for differentiability. So not differentiable at sharp corners, right? Not differentiable. Also at infinites, so like vertical slopes. So if this is literally vertical, because remember, like, we need to be able to take a derivative, and a derivative is essentially a slope, right? Now, what's the slope of something that's going straight up? It doesn't have a slope, it's undefined. So I'll draw that better. At sharp corners, at infinite slopes, what else is there? Like anything that's, well, first of all, anything that's not continuous is automatically not differentiable. So that's one thing to remember. Yeah, so sharp corners and infinite slopes, they're not going to be differentiable. So those are exceptions. I think there might be one more. I forget what the exact classification is. I think it might be like jumps. Or like a hole in the graph, but those are all not continuous. So if it's not continuous, it's automatically not differentiable. So also remember that. So you can look at these. Which of these have sharp corners? Which of these have like vertical slopes or like places where they're not continuous? And then it's not going to be differentiable then. Okay, determine if the function below is continuous, differentiable, neither, or both at the breakpoint. So this is probably where people are going to need a bit of help. I'm just going to do the packet problem up until the last like few steps, and then have you guys do it by your own, so I'm not just giving out the answer. Well, determine if the function below is continuous, differentiable, or neither. Remember, it might be a good idea to see if it's continuous first, because if it's not continuous, we already know that it's not going to be differentiable, right? If it's not continuous, it's not differentiable, because continuity is necessary for differentiability. It's required to be differentiable. So let's test for continuity. So continuity, let's remember the definition, the limit as x approaches a for f of x must equal f of a. Right? That is what we wrote up here. Right? The limit as x approaches a for f of x must be equal to f of a. So this also means the two-sided limit must equal f of a. So I'm going to just make that obvious. So the limit as x approaches a from the left must equal the limit as x approaches a from the right must equal f of a. Well, what is the limit as x approaches a from the left? Well, this is a piecewise function, so this would be the one place where continuity might not work, right? So x approaches a from the left of 0. So it would be, we plug in 0 into sine of x. So we would have sine of 0 is equal to, as it approaches 0 from the right. So we're going from the right. Oh, wait, actually, that's my bad. From the left, we have to be careful. So this is when x is less than 0. So from the left, right, here's where 0 is. From the left, that's when x is less than 0. So it's actually this function that we're plugging into this first one. So it'd be the limit as x approaches a from the left is actually 0 minus 3 times 0 squared is equal to the limit as x approaches a from the right. Well, from the right, we're looking at this domain, right, as x is greater than 0. Right, 0 is here, x is greater than 0, so it's all this range. We're approaching from the right. Cool, so we're going to be using sine of x. Okay, so it's going to be sine of 0 is equal to f of 0. Well, it has to equal f of 0, so let's just test that out. So 0 minus 3 times 0 squared, 0 minus 0, 0. Sine of 0, also 0. F of 0, well, let's plug f in. Well, okay, this is g of x, but same idea, f of x. So we're going to plug in 0 into this function. Well, where does it go? Well, this is when x is less than 0. This is when for x is greater than or equal to 0. So we are going to plug it into the sine of x. So that's actually going to be sine of 0, right? Well, what is sine of 0? We already saw it's 0. Okay, cool. So all these three are equal to each other. Cool. So it is continuous because our requirements are met. I just gave the answer. Well, whatever. So it is continuous. But now we're going to test differentiability. So differentiability is looking at the derivatives from the right and left. Remember? So that limit notation, the limit as h approaches 0. So what we're really looking at is, okay, f prime of c is equal to the limit as a, I'm just writing down the definition again, f of c plus h. Sorry, give me 1 second. Minus f of c all over h, right? Okay, so again, the limit as h approaches 0. So this, we're actually looking at this from two sides. So going from the left again, right? For this limit to exist, they must equal each other. From the left, the limit as h approaches 0 from the left of f of c plus h minus f of c over h. This is just a derivative from the left. Well, when we're coming from the left, again, we're using this function, right? What is the derivative of this? Well, let's do power rule. So we have 1 minus, we're bringing the 2 down, so it's going to be minus 6x, right? Now from the right, the limit as h approaches 0 from f of c plus h, oh, sorry, that's approaches 0 from the right, minus f of c over h. Now we're going to get, we're looking at the derivative of this piecewise function from the right. Well, from the right, we're coming from greater than 0, so we're looking at sine of x. Well, what is that going to be equal to? The derivative of sine of x is cosine of x. Now let's plug in our actual question, like, is it differentiable at 0, right? Because that's the question, because that's where this whole piecewise function happens. So let's plug this in. Equals 1 minus 6 times 0, so that's equal to 1, right? And then cosine of 0 is equal to 1. Okay, cool. Now everyone can tell me after doing that work, just plug in 1. Well, are they equal to each other? The two limits have to be equal to each other, left and right. must equal. So you can tell me if it's equal, then it's differentiable. If they're not equal, then it's not differentiable. So you can tell me based on that. Okay, find the values of a and b that will make the function h of x differentiable. So what we're really looking at here, right? Okay. Hint, if a function is differentiable, what else must be true? Well, that should be pretty obvious. If a function is differentiable, what else must be true? Well, it must be continuous. Well, if a function must be continuous, what is our definition of that? The limit as x approaches a, in this case for h of x, must equal h of a. So that's a two-sided limit again, right? Two-sided limit. So from both sides, I'm just going to try to write it out like bypassing the next step. So from the left, we have ax squared. This shouldn't be confused with this a. I believe they're different actually. But so ax squared plus 1, right? Okay. Actually, I'll just write it out. So the limit as x approaches a from the left is equal to the limit as x approaches a from the right is equal to h of a. In this case, our a is 1, right? This is kind of confusing because there's also an a in this equation, but they're different a's. So I'm going to say, just to rewrite all of this, so x approaches z. Z isn't used. This is just an arbitrary number. X approaches z from the left, x approaches z from the right is equal to h of z. Well, this is our point of interest, right? Because where would it possibly not be continuous or differentiable? It would be over here, right? Because this is a piecewise function. That's really what we're curious about, right? Because we're curious about at 1, does the function like perfectly meet up like this? And it looks like really pretty, it's continuous and differentiable? Or does it look like something messed up, like bam, and then like bam, like obviously this is not continuous and differentiable. So really we're curious about what's going on at x equals 1. So the limit as x approaches 1 from the left, right? Well, from the left, we have bx minus 3. So we're going to just plug in b times 1 minus 3 must be equal to the limit as x approaches 1 from the right. When x is greater than 1, we're using this equation. So a times 1 squared plus 1, right? And this must equal, well, the same thing because we're plugging in 1. When x is equal to or greater than 1, it's the same equation. So I can write this out again, but we don't have to. Plus 1, because these two are obviously equal. So the only question is whether these two are equal. Well, we're calculating for what they would be equal to. Oh wow, this is actually possibly harder than I expected. So b minus 3 is equal to a plus 1. Cool, but now we have 2 variables, so we need a second equation to solve it. So let's test for differentiableness. Test for differentiable. Okay, well, remember for a function to be differentiable, the limit, well, the derivative from both sides must be equal. So from the left, the derivative going from the left, right? So from the left, when x is less than 1, the derivative of bx minus 3, well, b is some number, right? So it's like, let's say it's 3x minus 3 just for example, then the derivative would be 3, right? Because just doing power rule. So in this case, the derivative would be b. From the right, the derivative is simply power rule ax squared, so it would be 2ax, and then the 1 between, so 2ax. Right, so now we know that for it to be continuous and differentiable, b must equal 2ax. So we have two equations now for two variables. Perfect, so we now have a perfect systems. So b is equal to, here I'm solving on the side, b is equal to a plus 4, just to simplify, and b is also equal to 2ax. So now I can replace a plus 4 for b here, right? A plus 4 just goes into b there. So we're going to get, well, actually, this is just a system at this point. I would like for everyone to solve after this point. Yeah, everyone should solve for b and a. I want everyone to do the work. And just a side note, I would expect everyone to show the work for this packet while they're working on it, show their work. Okay, derive the following functions. Make sure to employ power rule, chain rule, product rule, quotient rule, etc. when necessary. I'm going to change this to I'm going to change this problem to square root of t to the 4th cosine of t. Okay, so really with, let's say I'm just finding the derivative of this, my first instinct would be change that square root to a power. Okay, so now I can do power rule, right? So it would be 1/2, well, I'll just write this out more clearly, v prime of t will be equal to 1/2 t to the 4th cosine of t. And then power rule, so I'm subtracting 1, so to the negative 1/2. Cool, power rule. But I'm not done, right? Because there is variables inside here. There's a function inside here. So I need to do chain rule. So I need to multiply by the derivative of t to the 4th cosine of t. Well, that's all fine and dandy, but t to the 4th cosine of t, that's not exactly the easiest thing to take the derivative of, because I need to employ power rule. So it's actually like a double thing here. So let's just first find the derivative of t to the 4th cosine of t. So u is equal to t to the 4th, b is equal to cosine of t, u prime is equal to 4t cubed, b prime is equal to negative sine of t. So power is uv prime plus vu prime. So uv prime, so t to the 4th times v prime, which would be negative sine t. I'll write that out. Let's just write that out. So negative t to the 4th sine of t plus vu prime. So v is cosine of t. U prime is 4t cubed. So it would be 4t cubed cosine of t. Cool, so this is our derivative of the inside function. So we actually have to multiply this function, right, by the derivative. We're doing chain rule, the derivative of the inside function. So we're multiplying by this whole thing, negative t 4th sine of t plus 4t cubed cosine of t. Wow, that is a lot. If we want to simplify this, honestly, this is like, pretty sure this is the final answer you really need. But if we want to simplify this, we can make it clear so that all the fractions are in this. So the 1/2, that means 2 is at the bottom, right? 2 is at the bottom. Now t to the 4th cosine of t is to the negative 1/2 power, so we can bring it to the bottom. So t to the 4th cosine of t. And then it's to the 1/2, right? So that's the same as doing square root. That's a terrible square root, sorry. And then the top is still negative t to the fourth sine of t plus 4t cubed cosine of t. If you want to simplify it, that is what it would look like. Awesome. Now the next problem is like just as annoying, to be honest. So I'm going to do, how can I simplify this? Let's do, okay, there should be cosine of x first of all. Let's do x squared sine of x e to the x. Okay, well, the first thing I notice here is I'm almost 100% going to have to use quotient rule, right? There's a clear fraction. So let's try quotient rule. Yeah, this problem is annoying. So u, which is the top, is equal to x squared sine of x. That's easy enough. V is equal to e to the x. Also easy enough. U prime, well, let's actually just do v prime first is also equal to e to the x. The derivative of e to the x is just e to the x. So that's easy. Now u prime. So what's the derivative of x squared sine of x? Okay, well, looks like we're going to have to do another product rule to even get this derivative, right? To get this derivative, we're going to have to do product rule again before we can even properly do quotient rule. So it's kind of like this whole thing we have to figure out here. So we're doing like another product rule. So u in this case is equal to x squared, right? So it's x squared. V is equal to sine of x, right? U prime is equal to 2x, just taking the derivative of x squared. Power rule is 2x. V prime is equal to cosine of x. So u v prime plus v u prime. Cool, that's product rule. So it would be x squared cosine of x plus vu prime. So that's a terrible v, vu prime, b. So it ends up being 2x times sine to the x. So our u prime here is actually a whole long chain. It's x squared cosine of x. It's this whole thing over here is u prime. Okay, x squared cosine of x plus 2x sine of x. Nice. Okay, so now we have all the elements that we need for quotient rule, right? Now we need to actually do quotient rule. And quotient rule is what? Like vu prime minus uv prime all over v squared, I believe. So now let's just plug in those elements. So e to the x, right? U prime is this whole thing. That's annoying to write. X squared cosine of x plus 2x sine of x, right? Minus uv prime. So it'd be x squared sine of x times e to the x all over v squared. V squared is e to the x squared. It should just be e to the 2x. Remember when you're so you're adding, when you're squaring exponents, you're really just adding them. So we're doing basically e to the x times e to the x. That equals just e to the 2x. So this would be our final answer for this problem. You can distribute the e to the x if you want. Anyway, stuff like that. So these problems are kind of confusing for derivatives, but they're good practice. What else do we have to do? Oh boy, okay. So I don't know how I would. Okay, I'm going to try to do some of these and just adjust them. So let's do for number one, instead of x-coordinates of a relative minimum. We're going to do x-coordinates of a relative maximum. We're going from a maximum when we know f prime of x at a certain point, let's say at a certain point, f prime of x, right? So that's the slope, goes from positive to negative. We know this is a maximum because if you think about that, right, that means the slope is going positive and then it's all of a sudden it's going negative, so the slope is going down. Well, what does that create? That creates a relative maximum right there, okay? The idea is the opposite with the minimum. It would go from negative to positive. So it would go from negative to positive. That creates a minimum. But in this case, I changed the question to maximum. And where does this function go from a positive slope to a negative slope? Well, this is positive. Oh, cool. Now this is negative. Well, that's our answer. So where does it change? At x equals 0. So the answer is x equals 0 for maximum. And you can visually see that this point at x equals 0 is obviously a relative maximum. Concave down. Well, I'll write concave up. Yeah, I will. Wait a second. Is there a concave? Wait, this is kind of a weird question. If you get to this question, because I don't think there's a portion on this graph that is concave down, so I don't really remember how we did this in class. But concave up is when the slopes are increasing. So we have a slope here that's highly negative, and it's still negative here, but it's less negative, and it's even less negative here, and now it's 0. Now it's more positive, more positive, more positive. So you can see the slope is constantly, the slope of the tangent lines, right, are constantly increasing. So because its slopes are increasing, we know it's concave up from 0 to 6. So I guess it's kind of a trick question because I don't think there's anywhere where it is concave, where it's concave down. Now, it's important to make the distinction between when the slopes are increasing versus when the function is increasing, because you'll notice how, okay, well, you'll notice the function is going down here, right? Yet it's still concave up because the slopes are increasing. It goes from super negative to kind of negative to not even that negative. So the slopes are increasing even though the function is decreasing. Oh, wait. Oh, okay, this is my bad. Wow. Okay. Okay. So I did this, the first two problems completely wrong because I forgot that this is the graph of f prime and not just f. So do not make my mistake. Remember, this is the graph of f prime. F prime. Okay. So your thought process will be different for these, right? So I'm just going to go back and really quickly do what would happen if this was f prime. So remember the same idea. Let's see, maximum. Is there a maximum though? There's no maximum. Okay, so I'm going to just really quickly, it would be from when f prime goes from negative to positive, right? And where does it go from negative to positive? Well, here it's negative, here it's positive. So it's right here. So there's a relative minimum at x equals -3. In which case, concave up. So the slopes are getting more positive. Well, where are the slopes getting more positive? Well, graph f prime is the slopes, right? Is the slopes. Is slopes. And f prime here is going from 0, it's going from negative actually, to more positive, you can tell, because it's just increasing. So it's actually from -4 to 0, and then also from 3 to 6. -4 to 0, shooting with 3 to 6. Okay. Intervals on which f of x is increasing. Well, this is the graph of f prime of x. So whenever f prime is positive, and that changes to decreasing actually. Whenever f prime is negative, then we know that f prime of x is decreasing. Well, f prime of x is negative here, so -4 to -3. I feel like the rest of these, okay, so basically for these problems, I feel like most of everyone should be able to solve them. I might do a couple more. I'll do this next one. So f double prime of 3. So this is f prime of 3, right? So f double prime of 3 is just looking at, it's like taking f prime of this graph, right? F prime of this graph. So we'd be looking at basically the derivative at 3, and that's just the slope, right? So at 3, the slope is 0, so we know f double prime is also equal to 0. We're looking at the slope here. Let's see, intervals on which f of x is both concave up and increasing. Let me see which ones I should do. Okay, I'm gonna also look at inflection points. So inflection points are when concavity changes. So that would be when f double prime goes from f double prime of x, changes from negative, right, to positive, or from positive to negative. So f double prime changes from negative to positive. So now where would f double prime be negative? Well, we kind of just looked at f double prime 3. F double prime is would be the slope of f of prime. So I mean, f double prime would be positive here, right? Because the slope is positive. Be negative here, be positive here because the slope is positive, negative because the slope is negative. So, and then we know that inflection points are when it changes from negative to positive. So where would those points be on this graph? Okay. Let's do the implicit differentiation again. And okay, so I'm going to do probably these two example problems. Yeah. Actually, I'm just going to do this example problem, the second one, because the other ones should be pretty standard. But this one, you notice there's x and y, and they're multiplied together. So that's a good inkling. We're going to have to use product rule here. So I'm going to rewrite this as, let's say, 3x cubed y to the 5th minus 2x equals x squared plus 4y squared. Actually, 3y squared. Okay, so I'm doing this problem instead now. So we're differentiating both sides with respect to dx to x. So 3x to the 5th, y to the 3x cubed, sorry, going too fast. Y to the 5th minus 2x is equal to d over dx of x squared plus 3y squared. Cool. Now we're differentiating each term, so we can kind of separate all of these, but I'm not going to draw that out because that's too much right now. So first we're differentiating 3x cubed y to the 5th. Well, that requires product rule, right? Because we're multiplying these two variables together. So we're going to multiply 3 by the whole product rule. So in this case, u is equal to x cubed, y is equal to, not y, v is equal to y to the 5th, right? U prime is equal to 3x squared, v is equal to 5y to the 4th. Sorry. But we're differentiating y here, right? And remember, we're doing a mini chain rule. So every time we're differentiating y, but we're differentiating with respect to x, we can't just leave it as a power rule because we're not differentiating x, we're differentiating y, which is a different variable. So we're going to have to multiply this by dy over dx. Change y over change in x. Remember, because we're differentiating y to the 5th. Here we're differentiating x cubed, but since we're differentiating already with respect to x, we don't have to do anything, if that makes sense. But with respect to y, we have to multiply by dy over dx. So we're going to get uv prime plus vu prime. So it's u is x cubed times 5y to the 4th dy over dx plus the u prime, which would be y to the 5th, so 3y to the 5th x squared, right? Cool. Now minus d dx of 2 to the x minus 2 is equal to d dx of 2x plus d dx of 3y squared. So let's just do power rule, 6y. And then remember again, we are differentiating y with respect to x, so we have to include a dy over dx. Now let's simplify everything. So how should we do this? Let's divide both sides by 3. So x cubed 5y to the 4th dy over dx plus 3y, what is it? So 3y to the 5th. Okay, 3y to the 5th x squared. Divide both sides by 3, so it'd be minus 2/3 equal to 2 over 3x plus 2y dy over dx. Okay. So I'm going to move all the dy to the dx terms to one side. X cubed 5y to the 4th dy over dx minus 2y dy over dx is equal to 2/3 x plus 2/3 minus 3y to the 5th x squared. I just moved all the terms to one side. So I'm going to isolate dy over dx on the left side, multiply by 3x, 5y to the 4th. Or like factor out dy to the dx is what I mean. 2y is equal to, this side is the same thing that's here. I didn't change that yet. So then dy over dx is equal to, well, it's equal to 2/3 x plus 2 over 3 is the same thing as 3y to the 5th x squared, but then I divide this all by x cubed 5y to the 4th minus 2y. Kind of complex, but yep. Remember here we are differentiating. We had to use a power rule, and then within power rule we had to do the whole implicit differentiation chain rule thing, multiplied by dy dx. Now this problem, the final problem, we're also defining implicitly, so we have to do implicit differentiation for this. Let's see, I can show this really quick. So let's say it's y cubed minus 8x squared equals 9. Okay, so I'm going to differentiate this with respect to d over dx. Okay, so 3y, so we get 3y squared, cool, just power rule, but we're differentiating with respect to x. So what does that mean? Multiply by dy over dx. Minus 8x squared, power rule, 16x, and then this is an x though, so we're differentiating x with respect to x. So we're all good, we can just leave it like that. Now d to the dx of 9, derivative of any number is just 0. So then we move 16x to the other side, 3y squared dy over dx is equal to 16x. Dy over dx is then equal to 16x over 3y squared is equal to, I don't really think that simplifies into anything, so we can just leave it like that. Now, let's say below is a graph of the curve given in problem 1. So this graph is this equation. So it's not this one, so I can't really use it exactly. But the idea is, does your equation for dy dx support the location of the horizontal tangents drawn in the graph below? Well, where are the horizontal tangents? The horizontal tangents are, we can figure out the point. They're at x equals 0. Well, they're at these coordinates. X equals 0, y equals, what is that like? Let's just say it's close to 3, so 3, and 0, and -3. So does the equation with dy dx support the location of the horizontal tangents drawn on the graph below? Well, what does a horizontal tangent mean? Horizontal means slope. Slope is equal to 0, right? And dy dx is just a derivative, right? We calculated for dy dx here. And that's just the derivative, and we know derivatives are just slopes. They're just rates of change. That's what a derivative tells us. So basically our dy dx has to be equal to 0. Well, how can we test that? Well, we have our dy dx equation, right? In this case, it's 16x over 3y squared. Let's just plug these numbers, 0, 3, right? This is x and y. Let's just plug it in and see if we get 0. Do we get 0? If we get 0, then it supports the location. If it doesn't, if we don't get 0, then it does not support the equation. So yeah, that is how you do this problem. Trying to figure out. Okay, I'm gonna really quickly do a problem similar to this. Let's do either x plus sine, no, plus cosine y is equal to x squared, right? So we're differentiating with respect to x on both sides. Right, okay, sorry for the messy writing. D to dx, x squared, right? Differentiating with respect to x. Well, how do we differentiate e to the x? What's the derivative of e to the x? Well, e to the x, and notice it's the same variable, x and x, so we don't have to do anything else. The derivative of cosine is negative sine of y. Cool. Okay, but there's a y. So what do we do? It's not x anymore, so we got to multiply by dy over dx. It should be automatic. Every time that you see that, you just multiply by dy, or like d whatever variable over whatever variable you're differentiating with respect to. So in this case, those are y and x. Now d dx of x squared, well, with respect to x, so just do power rule equals 2x. Now you can just isolate d over dx, so 2x minus e to x, so 2y over dx, so 2x minus e to x over negative sine y. That's your answer. Okay, so I'm gonna scroll through this really slowly. You have time to pause at every moment if you need to. Sorry if my handwriting is kind of bad. I try to go through this quickly. If anyone has questions, again, feel free to email me because you guys have 2 more days to do it, basically. And I will be grading this for correctness. Generally, I will be grading this for correctness. So I would like for everyone to put their best effort to doing this. Email me, text me, whatever. And thank you to everyone.